Good morning, everyone. I assume you can hear me okay? Fantastic. Yeah, so exactly as Andre just said, I'm interested in sustainability of digital media. I work at the University of Bristol, of course, not just by myself. There's a team, the Sustainable Computing Research Group. So we're in computer science, in the Department of Computer Science. And so we bring an understanding of architectures, of how digital services are constructed, but we combine this with an understanding of sustainability. And over the next minutes, I'll unpack that for you, what that means. So a bit provocative. I know we're in the energy efficiency stream here, and I put this slide here to ask if efficiency equals sustainability. And that's what I've got here is from a recent paper from Christian Herglotz, who I thought might be here, but he's probably still in breakfast. And what we have is this, does that work? Yes. But now I can't get rid of it. I just took this graph from this paper where we describe how to measure power consumption for digital media, for digital devices in a robust way. And if we assume this is maybe a smartphone and, there he is. Good morning, Christian. Do you recognize that graph? You do, yes, exactly. Yeah? So if we assume that we've measured the power consumption of maybe some decoding task of a video stream on a mobile device, and we carry out some innovation, some new decoder, and we can reduce the power consumption maybe by 50%, as illustrated here, does that make us more sustainable? And I see some shaking of heads. Of course, we can't answer this question without understanding the context in which this service is being used. Yeah? This is ultimately, we can cast all sustainability questions within the frame of, when they come to carbon, what is its contribution to the cumulative carbon emissions by some time in the future, maybe 2050, 2100. That could be a measure of absolute sustainability. But if we're just looking at a digital service in isolation, we are sometimes at risk of losing this perspective. And I've got some conceptual framework that helps us understand the environmental effects of ICT here that I'll go through, and it will structure the rest of the talk. So this framework is not from me, this is from Lorenz Hilty from Switzerland, who is emeritus professor for sustainable computing. And according to this concept, we can structure the environmental effects of ICT in this matrix here of sort of two dimensions. On the one, there's the environmental impact of ICT that is negative for the environment. So that's the red column here. And in the first instance, here's the reference, this refers to all of the impact from making the devices, from using the devices, and from the end-of-life treatment of devices. This is what we call the direct effects. And they're always negative. There's no way, if we're just looking at the operation of the device, for that to be positive for the environment. Because, as we know, the question, if something is positive for the environment, it would result in reducing the carbon emissions by 2050 or 2100. Yeah? So these are always negative. It is possible that ICT services have a positive contribution if we're looking at what we do with the technology, the enabling effects. And then we can ask if a service results in the substitution of another existing activity in the economy or an optimization. A substitution, for example, could be the use of a video conference instead of physical travel. We can claim that we're getting the same kind of service out of this, but we're no longer traveling, we're no longer using a lot of electricity for moving physical stuff through the world. Or we're optimizing something, then the service isn't replaced, but we're making more efficient use of resources. So these are the two dimensions here: the enabling effect, the direct effects, the enabling effects, and the systemic effects on the third level, where we're asking, after we have applied this technology within the context of some service, how will it change the way that society and economy are structured? So, for example, these are paradigmatic transitions, such as a sharing economy, where digital technology enables the sharing of cars, for example, in an agile way, and that has a fundamental effect on the structure of the economy. So these are those three layers, and in both cases we find either positive or negative effects. Okay. So we can apply this direct perspective now and look at the contribution of the ICT sector specifically to anthropogenic greenhouse gas emissions. That's what we've got here. So roughly, as a global society, we're emitting about 50 gigatons of carbon every year, and the ICT sector is part of this economic activity. And we can sort of, it's in the region of 2 to 4%. It's uncertain because the data isn't perfect, but this is roughly the current opinion of how much digital technology contributes to global greenhouse gas emissions. And we can drill into this a bit more and ask, within the ICT sector, how do the various subsectors contribute to this? This data is a bit older. Data centers in this data, they are still contributing to one of the smallest impacts. As you know, that has risen considerably, but still it will not be more than the private, the user devices in houses. TVs in particular are very energy intense and more than data centers. So this is an aggregate perspective. But as André said, when I started work in Bristol, one of the first things we did, we carried out an assessment for the Guardian newspaper. They wanted to understand what the transition from physical to digital means for their organization, for the sustainability of their organization. And this service-based perspective is essential when we're trying to help organizations in becoming more energy efficient, becoming more sustainable. So I'll spend a few moments talking about this. And services is what we're very familiar with. Much of the work that's taking place in this community is about enabling digital services. And in order to use life cycle assessment as a disciplined approach to study the environmental impact of a service, we are looking at a perspective that is comprehensive in its system boundaries. That is including the architecture of the service. So we want to take into account user devices, we want to take into account networks and data centers. But it is also comprehensive in the sense of its life cycle, meaning we want to take account of the manufacturing of devices, getting materials out of the ground, transporting goods and services. All of these economic activities are associated with environmental impact. And we want to take care of the use phase. That's the thing where energy efficiency matters most. And then what happens at the end of life. And that's what life cycle assessment gives us, a disciplined approach to carrying out an assessment according to this structure. And the term life cycle comes from the ambition to revert the outcome of the end-of-life treatment, the material, back into earlier life cycle phases. And we want to close the loop. Many of you will be familiar with circularity principles. That's the ambition, that's what we're aiming for. The reality is that in the current economy, we're not recovering a great deal of the material that goes into electronic devices. But ultimately, that's where we want to get to. And then within each of those life cycle phases, we understand a service as a sequence of processes up there in the corner. And for each process, we're tracking how much energy is going into that, how much waste comes from it, and how does this process contribute to the product that we're studying. Yeah, so then the process could be encoding a video in a data center, or it could be finer than this, more fine-grained. One of the things that we did in Bristol is build a reporting tool for the media sector called Impact. And these organizations are using this to calculate what are the carbon emissions from delivering their services. And reporting is one thing. This is calculating a number that they can then communicate to their audience or to other stakeholders who want to understand what's the environmental impact of the service. The next thing is making a difference to how the service is provided, and I'll come to talk about this in a moment. But just as an example, this is maybe just about readable in the first row. This is an illustration of this idea that we are studying an architecture of a digital service as composed from several processes. So when we built the Impact tool, we spoke with the media companies that you just saw, and we understood what is the architecture of delivering these services, and we abstracted from this to have a canonical, generic architecture like this. Yeah? And we want to understand, for example, the variety of user devices that are being applied by the audience, because the energy consumption between those devices varies, and so that matters. We want to understand how are those services delivered over networks, and we want to understand what's happening in the data center. So that's the direct perspective. One level up, we already spoke about this, are the indirect effects of digital services. And one of the examples is that we are using digital technology to substitute physical processes. Home working, for example, instead of traveling to work, is made possible via video conferencing. And we can ask, what are the effects of this? And in the first instance, there's a substitution taking place. We're not traveling in the car. We're using electricity in the home. The devices have to be made for us to be there. The networks have to be running. And the data centers need to be there. And we can calculate the balance between those processes in order to come up with an environmental assessment. Yeah. Importantly, when we're moving on to the systemic perspective, we need to take into account that user behavior is complex. And actually, there's a chain of effects that is taking place. In the first instance, we're enabling workers to stay at home instead of traveling. But over a longer period of time, we use that flexibility to live further away in a more pleasant environment. Yeah? And then we might still come into the office now that we're being called back into the office and we have to travel. And maybe all of those claimed benefits that we had anticipated from substitution of travel, they all evaporate. Yeah? So it's complicated to make a net impact assessment. And that's what this slide here is about. If we want to make a claim about the net impact, positive or negative, then we need to basically carry out a line of reasoning that takes this into account. We want to look at the direct impact, so this is in the context of AI here. So that would be the energy consumption and making the devices. Then there will be some positive effects. In the context of AI, this might be the substitution of a translation task or some other text generation that we're no longer manually carrying out, but we're asking the computer to do for us. But then there are also indirect negative effects. Maybe because we're faster in doing it, we'll be generating more content of this sort. And we need to take all of those three aspects into account in order to calculate the difference between the before and after. What we're constructing here is a counterfactual, because we can never have both worlds. We cannot study a world in which we have AI and in which we don't have AI. So we always have to make assumptions. What we're usually modeling is a business as usual, and then we're introducing a service, and we're making some assumption about how the energy consumption of that service will be, and how consumers will respond to it. And that's necessarily uncertain. And I want to come back to this in the context of ISO. And we can have new uses that we didn't think of. Yeah? So AI might enable autonomous cars, and suddenly it's possible for our pets to go to the doctor themselves. I want to come back to the carbon emissions of video streaming. So starting from the perspective of calculating energy consumption across this end-to-end architecture, data centers, networks, and user devices. Here are examples of work we've done for the BBC, and over here, this graph. And we've broken this down via different parts of the architecture and how they contribute to the overall energy consumption. And we can talk about this. For example, we can talk about this afterwards. Why that might be the case. We also, I know it's very hard to see, what we've got here is the energy per device hour. So roughly your energy intensity while consuming BBC iPlayer between terrestrial broadcast, watching it over cable, over satellite, or over streaming. And we can see here there are different energy intensities. And you might think then, okay, iPlayer obviously is much higher, about 180 watts per hour, watt-hours per hour, so 180 watt, versus terrestrial, about 60, so a third. If I now decide not to stream, but instead watch something via terrestrial, or the other way around, then I have a real lever to be more energy efficient. I can make a real change, yeah? 3 times difference. Sadly, that's not the case, because the majority of the infrastructure where the environmental impact is lying is independent of our use. If you decide to stream something over the internet or not, the networks are always there. They're always on. And as we'll see in a moment, the power consumption by networks hardly changes at all. This tripped us up. In 2019, we carried out some modeling work of YouTube. We built the global delivery of YouTube, and then and calculated out this distribution and the contribution. And then we thought, oh, anecdotally, we can see sometimes the youth, they are watching YouTube just to listen to the music. They're using it like Spotify, but for free. And the phone is lying there. No one is looking at the phone. They're just listening to the music. What a waste. And all those bits are being transferred and we're not consuming it. If we are cutting out the delivery of the video stream and we have a button to just deliver the audio, wouldn't that be good for the environment? So that's what we did, calculated if just from the part of the audience that consumes music videos, not all the others, but just the music videos, if 50% of the audience used this new service, this audio-only service, the carbon reductions that we calculated is in the order of 600,000 kilotons. That's about as much as the city of Glasgow in its entirety consumes per year. So that's worthwhile doing. The problem is, we were naive when we carried out this assessment for the same reason that I just mentioned. And actually, what we need to carry out is a change-based assessment. We need to understand how, across the whole architecture of the service, how do the individual processes respond to a change? That's the most important bit. So, when we're looking at networks, this is a very typical picture for routers. What we see at the bottom, this blue line, is the diurnal variability over the course of the day of demand, of throughput. Yeah? So it's probably readable at the back. Throughput varying between 25 to 125 gigabit per second over the course of the day. And we see the associated change in power consumption, which there isn't. Yeah? So, what does that mean? What do you do with this? This is in the home. I mentioned before, I drew attention to the customer premise equipment energy consumption in the BBC example. This is a box standard Wi-Fi router in the home, and we stress tested this with a variety of different things. 4K video streams. We had a recent experiment with a up-to-date router, several 4K video streams in the house, no change at all to the power consumption of the router. I'll skip over this, I might come back. What we're observing here is the power consumption of the infrastructure remains the same. At the same time, we know throughput in networks is increasing. Yeah? Data volume is increasing, but data volume is just a function of throughput over time. And curiously, the peak to mean ratio between, or the difference between the peaks and the mean throughput is increasing. Our peaks are getting peakier faster than the average data volume in networks grows. And that is important because if you're operating a network, and the same applies to servers, if you're operating any infrastructure, the capacity of this infrastructure needs to suit the peak demand. So, if that difference accelerates, our use of the infrastructure becomes less and less efficient. And conceptually, we can look at this like this. Traffic varies, goes up and down, not just on a daily basis, but also on a seasonal basis. But largely, it's going up. And capacity has to keep up with this. Because if the capacity doesn't, then quality of the user experience stops. At the same time, innovation in technology, if it's Moore's law, if it's innovation in better middleware, if it's innovation in better models, better applications, is always going up. So while we have to deploy more routers, more servers in order to provide that capacity, those new devices are also more energy efficient. And the interesting question is, how does the interplay between the efficiency improvements and the increase of capacity play out in the real world? And it's very curious. This is from BT, which is one of the main ISPs in the UK, comparable to the telecom in Germany. And there are two graphs here. The yellow line that goes down is a legacy network. That's the DSL-based copper network. And they're commissioning this as they do everywhere else. So that energy consumption goes down. And the green line is the strategic network. That's the fiber-based network. And that's going up. And the balance between the two of them is roughly stable. There's a 4% increase year on year, despite a 25% increase of data volume transferred. Yeah, so we can see that the efficiency improvement of the hardware is roughly helping to keep energy consumption in fixed networks stable. If we're looking at mobile networks, that is a different picture. Energy consumption in mobile networks goes up much faster. And when we are, this is from a recent paper in which we were asking the balance between those effects, really, if we wanted to predict what the energy consumption of a service is limited. So with Andre yesterday, we spoke about limiting factors on user behavior. And if you remove a limiting factor, then the consumption of the service would scale up, would increase. And the question is, how does this result in change of energy consumption? And here we were asking, how does the energy consumption of the router, what constrains this? What are the limiting factors? On the one hand, we've got a certain demand at peak time. And this demand at peak time is composed of mainly two types of demand. Your average daily up and down of demand that is regular. It could be your Netflix peak at 8 o'clock. On top of this is all of this sporadic peak in here of those events. Yeah? Live streaming, live events, games downloads. They are growing, and they are now the main driver of capacity increments, because they are growing faster than the average data volume. But that by itself doesn't explain, or it won't be predictive of the power consumption in the network, because it is equally constrained by many other things. For example, resilience requirements. The regulator in the UK is Ofcom, and they are mandating a certain robustness, a certain resilience to the network. And that comes with a loss of energy efficiency. You can't operate the network as lean because you need to be resilient. And now that network infrastructure has been termed critical, national critical infrastructure, the demand on resilience is increasing. The problem is that from an engineering perspective, when we're, so from a for example, computer science perspective, we are very good in modeling quantitatively how services change in the technical domain. The evidence that we've got here, these resilience requirements, they influence the service via a different kind of effect mechanism. If you go into an organization and you ask, to what degree did the resilience requirement result in energy consumption in the network, they wouldn't be able to quantify this effect in the same degree that the capacity requirement is deterministic and predictable. Yeah? And this is true maybe for resilience, it's easier, but there are other things like the physics of the material and technology. So innovation in this space, in the background, BT will innovate, they have R&D, but it's very unpredictable. So it's very difficult to quantify to what degree this results in efficiency improvements and accounting for this. What we can do though is from this model, from this observation that it is peak demand that is most determining on the capacity and hence the energy consumption, we can observe that outside of periods of peak demand, our energy consumption is still flat. And so now, if we wanted to attribute energy consumption to the use of the network by the services that are being transferred during that time, we would get an energy efficiency curve that looks a bit like this. Yeah? If I'm using a service at off-peak time, during this time when very, very few users are in the network, my share of the energy consumption would be extremely high. Now, I'd be burdened with a much higher energy intensity than if I was using the service here outside of peak. That is then when we're using the normal energy intensity that we apply for calculating the carbon emissions or for energy consumption of digital services. But actually, what we want to do is we want to incentivize demand shifting. We want to do exactly the opposite. We want to say that everything that is outside of peak comes for free, because the effect on the expansion of the network is squarely focused on services that are using the network at peak time. Okay? So why are attributional approaches so pervasive? Now, we find these everywhere. As I said before, when we carried out this model of YouTube, we used an attributional approach. And one of them is that a coefficient that you calculate from energy consumption of a network relative to all the data that is being provided, that looks exactly like the slope of a linear function. And so you can't help but interpret it in this way. Yeah, so that's one of the first things. We are assuming that efficiency can be applied to extrapolate energy consumption. Secondly, the marginal drivers, if we wanted to ask the alternative question of consequentially, what is really making a change in the network, then suddenly we need to step out of the purely technical domain and we need to engage with processes that are maybe in the economic domain or user behavior, and they are uncertain because sometimes they're subjective, and they are uncertain because we might not have the data. Yeah. I want to stop here and then use the rest of the time for questions. Thank you.